In this series of videos I'm attempting to repair and restore a DEC PDP11-34A vintage computer. In the videos so far in this series I've tried to run the machine, it wouldn't do anything, so I've stripped it down. I've set up a backplane and the power supply as a test jig along with the console. The console wasn't working, so I've repaired that, got that working, and I'm using this setup to test the individual boards before I start reassembling the machine. And it's a very nice way to test boards, it gives you full access to them. And in the previous video in this series I showed one of the serial boards, and in this video I was going to move on and start testing the memory card, so we'll do that later on in this video. But before that I've been asked to give a bit more information on the serial card and specifically show it receiving data. I only showed it transmitting data before. So before we get on to that, just a quick note that I've replaced the 8008 processor on the interface card for the console, not because this was faulty, but these are fairly rare, so I've replaced this Goldcat one with a generic cheap replacement, and I'll keep this one for Sunday best. I've also been asked to identify the cards that I'm dealing with. If you're familiar with these machines, I'm sure you recognise them, but for some people that haven't seen these machines, it might be useful to know what these cards are. So firstly we have the M9302, that's this bus terminator card, and it's just there to give some pull-ups and load resistors for the bus, and also it's a kind of backstop for certain signals that are required for the bus to operate. It needs to be there for this test jig or we'll get bus errors for no reason. We'll get bus errors anyway if we try to access something that doesn't exist through the console, but we'll get bus errors every time if we don't put this in, because there'll be nothing to pull up the lines. In fact, the system won't run without this fitted at all, because the bus DC low and AC low lines won't be pulled high, so nothing will come to life. So we have the console interface and keyboard and its controller card, and that's the one at the back of this pair. The one you can see is the serial card, but the interface card is a KY11LB, and that's designated as an M7859. And then finally we have the serial card, which is the one that we're looking at, and that's a DL11W, or designated as M7856. And I've also been asked to just clarify the way I have this hooked up. So it's going through to a terminal program on a PC. I'm just using a standard interface here. I've got a breakout board here just so I can connect a scope. But the TX and RX lines and the ground lines are connected, and they're going through to pins 2, 3 and 7. But the way it's connected, so if we look at the schematic, this is the connection part of the board, so that's just what connects to this blue connector at the top right. The top sections are for current loop, so the board supports TTL input, plus or minus voltage input for RS232, but also current loop input, and it connects as a source or sink for the current loop as well, depending on how the configuration switches are set. But the part we're interested in here is the connections that allow us to connect to a PC through into a terminal program. So what we're looking at here are connections F and J. So the F connection is an output and the J is an input, but notice that the J goes to a device but then loops back round back out to the connector. So that's this device here. It's just basically the standard transceiver chip that's used in an RS232 system, so very common 1489 chip, and we have a 1488 for the transmit. But it comes around to connection M, but then if we look down here, hopefully you can see it, it says TTL serial data in, and that's going to connection E. So all we have to do is, this line comes from our PC, and that goes through this buffer, and it comes back round to pin M on this connector, and we have to loop that round to the TTL input, which is where we want to feed the data in. which is pin E. So I've got I don't know if you can see it, there's a link here that joins M and E, so it's just looped straight round, and that just feeds our incoming data into the TTL input. Before we go on to test this, one other point that came up is actually a comment on a different project I'm working on, but I thought I'd clarify it here. It was about the RTC, and that can cause a bit of confusion because of the term RTC, or real-time clock. If you're used to dealing with modern processors and modern systems, RTC or real-time clocks are normally something that keep track of time and date, and they have usually a little clock crystal, or they're derived from a system crystal that gives a very specific time interval. Real-time clock on the PDPs was slightly different, or very different. It was normally derived from the mains frequency, so it was an input taken from the incoming mains AC. It was fed into the system, squared up, and that was done by the power supply. It's fed out as the LTC signal onto the main bus, and then that goes into this card, and it's squared up again, and it's used as a basically a source for various timing events. But it runs at mains frequency. It says here LTC, bus LTC low, and that comes in here, it's squared up and then fed into the system to generate regular time events. So that's what the RTC is in the PDP machines. It's not like the RTC in a more modern machine or more modern device. Okay, so on to testing this. I'll go through this section fairly quickly. I went through it yesterday, but we'll start the console up. So we'll power up the machine. We'll get the software into its correct mode by going through diagnostics and then immediately exiting. We've got our bus error, we'll clear that. I'll now bring up the console in the corner of the screen again, and I'll start by repeating what I did yesterday and sending a character through to the console. So as I said yesterday, the interface, there are actually 5 registers or addresses that we can access on this interface card. One's for the real-time clock, which we won't go into in this video, and then there are 2 for receive, 2 for transmit, and they start at 777,560 and go up to 777,566. We'll start off with the transmit. The transmit status register is at 777,564, and the transmit buffer, that's what we have to load to send data, is at 777,566. So we'll load that as an address. So to load an address, we just enter the address that we want. It's octal, of course, 777,566, and then we just press LED, load address, and we can now look at the address that we got loaded into the address register of the console. So if I press display address, hopefully you can see it's saying 777,566. So I'm hoping you can see this okay. What we can now do is send data out to that address. In this case, we'll send the code for an uppercase A. So 000101, and if we hit deposit, that will send the character. And as you can see, the character has appeared on the console. And we can just keep repeating that. So if we look back at the address that we want, and the way this console works is if we just keep hitting deposit or examine, it will increment the address. But if we hit display address, it reuses the same address we've already entered. So by just hitting display address, it saves us having to type the address back in. And what we can then do is send out another value. So in this case, we'll send out an uppercase B. And as you can see, that's appeared on the console. If we want to receive, then one thing I'd say here is this kind of setup is useful not just for fault finding and fixing boards, but also learning how the cards work, how to write software for them, and it gives you good understanding as to how the system operates if you're not familiar with it. So for example, if we want to receive data, there are 2 registers involved. There's a status register and there's a buffer register. The status register, amongst other things, will indicate if there's any data in the receive buffer. and there's a flag. Bit 7 is a flag that's set whenever data appears in the receive buffer, and that status register is at 777560. So if we enter that as an address, 777560, load the address. So if we display the address, you can see that's what is now loaded into the address register. And what we can now do is examine that register. So if we hit examine, notice it stays at 0. So there is no data in the receive buffer, and that is indicated by the fact this value is 0. But if I now send a character from the terminal program, then we will re-examine this register, and we should see that the flag has been set to indicate that we've received some data. So I'll send a character. I've got local echo set on the terminal program, so we'll see the character appear there. But that's not coming from this end. It's not echoing the character back. It's just I have local echo set for the terminal, so we can see it. As you can see, I sent an uppercase H, and if I again press display address to make sure we retain the same address, so this is the status buffer, and if we now examine that address, notice that we're getting 200 octal, meaning that bit 7 of the register is set. And we can keep examining this as much as we want. If we keep looking at this same register, so if we were writing software, for example, we could keep examining this register to see what was there. We'll retain the same address, examine, and the flag stays there, and we can read this as often as we want. We can read the status register and it won't change the status register. What we can do is either type in explicitly the address of the receive buffer, so I'll do that, 777, in this case it's 562, it's the next register. We'll load that address, and if we now examine that, notice we're getting a value of 110, and that's the octal value for an uppercase H. But if we now go back, and if we go to display address, we're at 562. But if we go back now and look at address 777560, I'll load that address, and if we now examine this, notice that the value is now 0. So although we could read the status register as often as we wanted without changing it, as soon as we read the actual data that's been sent by reading the buffer, it clears the flag. So that's how you clear the flag. You can explicitly clear it, but if you read the data, it clears the flag, and that tells the system that it's ready to receive the next data. And that's how you go about designing a system like this or using a system like this. So if we look at the displayed address, we've got 560, examine. If I send another character, so this time I've sent an uppercase K, and if we look at the address we're currently have loaded, it's 560. If we examine that, notice the flag is set again. In this case, rather than typing in the next address, I'm just going to hit the examine key again, and that will increment the address and show us the value there. So this time we've got 113 octal, and that is the value for an uppercase K. So you can see it's a very good learning tool. It's a good way to get an understanding as to how the cards work, and that again can be very useful in figuring out how to write software for them. Okay, so hopefully that's explained a bit more about this card. If you want me to go into more detail, then leave a comment, but what we'll do now is I'll take this card out, I'll put the memory card in, and we'll see if the memory card works. That is obviously one of the bigger headaches in getting these machines working, is getting the memory card to work. So that's the next one I intend to look at. So I'll get that plugged in. I have the memory card plugged into the backplane. I've taken the serial card out, and the reason for that is I don't want too many cards plugged in. I don't have the fans running, and the memory card in particular draws a lot of power, so it's going to draw maybe around 10 amps from the 5 volt supply, and I don't want to put too much of a load without the fans running. So there's this particular regulator, the second one back, I need to keep an eye on the temperature when the fans aren't running. It should be okay for a while, but I don't want to push my luck with it. Testing memory cards is often a bit of a pain, because just it's the sheer number of ICs on here that can fail, and memory chips are fairly notorious for failing, especially when we have supply issues. I think this machine was okay. I don't think there are any major supply issues. It was coming up with an issue, a fault indication, but I don't think it was because the actual supplies were faulty. I think it was just a poor connection, but I think the supplies themselves were okay, so I'm hoping this card will be okay. The memory chips on this are HB8116s, and they are 16K by 1 bit. I've got no idea what this board is or who made it. It's not a DEC board, I don't think. If you have any information on this board, then please let me know, but I just want to see here if it works. Now, I've had a quick look at it and a poke around, and as far as I can tell, these switches down here are the ones that determine the address it's mapped to, and they're all set such that I think it's mapped from address 0 upwards. So that's what I'm going to assume to start with. If it's not, obviously it's not going to work, but we'll give it a go and see if it works or not. So I'm going to power this up. Obviously if it doesn't come to life we'll power off, but I'm hoping it's not going to stop the console starting up. It shouldn't do, it should work fine without the main processor fitted, but we'll have to see if it behaves itself. So we'll turn this on. Usual bus error, so we'll clear that. So the console seems to be working, and what I'm going to try doing is writing values to the memory address, or one of the memory addresses that should be in this range, and one that should be in the range is 0. So we'll try writing some data to that. So we'll load an address of 0, know the address, just check that, so display address is 0, and we'll try writing a value of 1, 2, 3, 4, 5, 6. We'll deposit that, and in theory that should have written a value to that address in memory. So display the address again, save me typing it back in, examine, and it is showing the correct address. But just to make sure this is not something we're buffering internal to the console, shouldn't be, but we'll just check. We'll try writing something to a different address. So we'll try 100,000, load the address, and if we now write a different value to that, we'll write all ones, for example, deposit that. And if we now look at the displayed address, we're at 100,000, we'll examine that, we've got all ones. If we go back to 0 address and examine that, we still have 1, 2, 3, 4, 5, 6. That's promising so far. We'll try another address, try 200,000, and in this case we'll set 1 and then all 2s. Deposit that. Okay, and we'll go back to address 0, examine that. We'll go back to 100,000. We have all ones, which is what we should have, and now we'll go up to 200,000, address 200,000. Examine that, and we're getting what we'd expect. We'll try one more address. We'll go to 300,000. It should incidentally go right up pretty much to the full extent where we get to the in-out system. I think this will give us a full complement of RAM on this particular machine. So in this case we'll go to 1, 3, we'll set all 3s, deposit that. We'll go back to 0. We've still got the right value there. What I'm looking for is kind of rogue values, or just not writing at all, and that will indicate whether we've got one or more failed memory devices, or if there's something wrong with the decoder logic. So that one's fine. We'll go to the next address. So if we go up to 100,000, and that's still correct. 200,000, that's still correct, and 300,000, and that's correct. So it does appear our memory is working. So I mentioned this bus error light, and it will illuminate if you try and access a register that isn't implemented on the system. So it's a good way of testing what your maximum RAM is. So if we try entering 700,000 on here, so if we enter 700,000, load that as an address, examine it, that's a good indication that there is something there. In this case it will be RAM, and you can keep incrementing the value until you get a bus error, at which point you've probably tried to access something off the end of the memory space, and it's a good way to determine where your memory ends. So it's looking very promising. I haven't seen any bit errors in this yet. We'll just try one more time. So 0, the address is still correct. 100,000, it's still correct. That's correct. And we'll do the last one at 300,000. And that's also correct. So it's looking like this card is actually working, which is a bit of a relief. I didn't really fancy going through this. I will be testing this in much more depth. And what I generally do is for each location, each major bank, I will test each individual bit. So I'll set values, data values, that exercise each bit in turn, and make sure that I can turn the values on and off. The easiest way of doing that, of course, is to set all ones or all noughts. Normally I'll leave it running for a while doing that, and later on we can enter, once we've got a processor in here, we can enter a program to properly test it. But this is a very good way of testing it, and more specifically, if we did find a fault, it's a very good way of isolating the fault, because we can carry out some very specific checks, and we can continually write to exactly the same address with the same data. You can of course do that with it in the system, but having it like this, where you have full access and you don't have the encumbrance of having the main processor working, makes things very much easier. Okay, the regulator's getting fairly warm, so I'm going to call this quits. I'll be fitting the fan to do more testing. I won't do that on camera because you won't be able to hear me. But hopefully you can see that this is a good technique to use for testing the boards. As I said, if you had an issue with this, it would be very easy to get a scope out and start looking around. And one thing you can do is put a test clip onto one of the chips in each row and put a scope on it, and then you can figure out which particular row and which particular chip is causing the issue by seeing if it's being accessed when you write data to a particular address. So it's a very easy way, simple way of fully testing a board like this that would otherwise be a bit of a headache to do. Okay, I hope you found that interesting. In the next video we'll move on and look at the next board.